Hello, class. Can we hear? Can we hear? Can we hear? Okay. So, sorry for the break. We couldn't hear ourselves from the explanation. So I think the network is better now. Can we hear ourselves now? Please, if you are online, just press I so that I will know you are present. And please, this class is very important for all of us to understand our nuclear chemistry before we resume. Can we understand now? Okay, can we hear each other now? If you can hear me, just say hi. Okay, thank you. Thank you. So, for the sake of those that didn't meet us when we were talking about nuclear reactions, I'm going to take that all over again. I'm going to take that all over again. Okay, so let's continue. I said we have alpha particle, which is alpha radiation, beta radiation, and gamma radiation. And we are going to classify this radiation based on their property. Based on their property. For the alpha has a positive charge. Alpha has a positive charge, but beta is negatively charged. Beta is negatively charged, but gamma has no charge. Gamma has no charge. The mass number for an alpha particle, mass, when I mean mass, I mean the weight. The mass is classified as the what? The weight. So per gram, the alpha is 6.64 times 10 raised to the power minus 2, which is the same mass of a proton, which is the same as the mass of a proton. Because it is positively charged, it takes the mass of a proton. Then beta is negatively charged, so it takes the mass of an electron. And what is the mass of electron? The mass of electron is 9.11 times 10 raised to power minus 28 gram. The mass of a beta particle, which is the same as the mass of an electron, is 9.11 times 10 raised to power minus 28. But our gamma particle has no mass because it has no charge. It has no mass because it has no charge. Then penetrating power. The alpha particle penetrating power is 1. That of beta is 100, but that of gamma is 10,000 and above. 10,000 and above. Then I said alpha particle can be stopped by a tin paper. Alpha particle can be stopped by a tin paper, but beta particle is stopped by aluminium. Beta particle is stopped by aluminium foil paper. Aluminium foil paper. The mass of alpha particle is 6.64 times 10 raised to power minus 24. I'm saying this because of Esther Oyinbo. The mass of alpha particle is 6.64 times 10 raised to power minus 24. So back to where we were. The gamma particle can be stopped by a lead concrete. You know when you make block, you put the block in front of the rays, it will stop. It will not be able to penetrate the gamma particle. Then what is the nature of alpha, beta and gamma? I said the nature is, how do you know that this is alpha? How do you know that this is beta? By the symbol. I said alpha is helium. You can use alpha, you indicate it by putting this symbol, you say it's alpha. Or you use helium symbol. Helium is He, you put 4 2, you say it's what? Alpha. But beta, for beta, you represent beta with this symbol. You put -1 and you put 0. That is what? Beta particle. Or, and for gamma, which is gamma rays, it is represented with Y. No charge, no charge, no mass number, no atomic number. So that is how you present gamma and what? Beta and alpha. So you see the top left of the board, you see that alpha, beta and gamma, the symbol for alpha, beta and gamma. Then how do we now do the reactions? How do we do the reactions? The one on the board is the reaction of alpha particle. I said the chemical reactions are quite different from nuclear reaction. In chemical reaction, we look at the number of moles, that is the stoichiometry. But in nuclear reaction, we are looking at the neutron to proton ratio. The neutron to proton ratio, the isotopes of the compounds. Are you seeing? Of the atom. If I'm using compound, please know that it's atom or element I'm talking about. And most of the elements or atoms that undergo radiations are usually the D block. From your periodic table, you know we have the F block and D block, the natalites, the antilines and all that. All those undergo radiation because their atomic number is above 80. So we look at it as not being what? Stable. Now, that does not mean that atomic numbers of less than 80 cannot be radioactive. So at those compounds that are less than 80 that are radioactive, that is why we said we use the neutron to ratio, neutron to proton ratio. And what are the neutron to proton ratio? What can we say? If neutron to proton ratio is equals to 1, it means the atom or the element is stable. But if it is greater than 1, it is not stable. And how do you calculate the neutron to proton ratio? How do you calculate the neutron to proton ratio? Okay, so I will do that on the board now for the sake of those that didn't join us on time. Neutron to proton ratio. How do you calculate neutron to proton ratio? So if we have carbon, I'm using carbon because you can use any element. You can use carbon, you can use nitrogen, any element or atom that is less than 80. How do you know that is radioactive? The normal element is 12 and 6, but an isotope of carbon is 13 and 6, 14 and what? 6. Isotopes means they have different mass number but the same atomic number. So how do you now know that this is stable and this is not stable? We have nitrogen. Nitrogen is 7, 14. Nitrogen can be 15 and 7. Nitrogen can be 17N7. So how do you know it is stable or it is not stable? 12 minus 6, atomic number, mass number minus atomic number is equals to number of neutron. Number of neutron. So 12 minus 6 is equals to what? 6. 13 minus 6, the number of neutron here will be equal to what? 7. And 14 minus 6, the number of neutron for this isotope of carbon is equals to what? 8. Now proton, neutron to proton ratio means 6 of the number of neutron all over 6 of the number of proton is equals to 1. So that means this compound is stable. But 7 over 6, 7 is the number of neutron for this isotope of carbon, and 6, which is equals to 1.2, so or 1.1, 1.18 or so. So you see it's greater than what? 1. It's greater than 1. But when you come to 8 over 6, you have it as 1.33 or so. 1.33. You see that it's greater than what? 1. So this compound tends to be radioactive. That means this atom, this isotope of carbon is radioactive. But this one, we may decide to call it radioactive or not radioactive. How do we know? If you do the proper mathematics, 7 over 6, 6 divided by 7 is 1 remainder 1. Add 0 to it, 6 divided by 10 will give us 1 remainder. Are you seeing it now? 1 remainder 4. Divide 6 divided by 4 will give us what? By 40 will give us what? That will give us about 7. So it's 1.7. So we know that we cannot say this is 1 point what? This is 1.17 or 1.8. So this can be classified as what? Unstable. Unstable because it's greater than 1. But let's assume that it's 1.05. Can we say that it's unstable? No. We can only say that it's what? Stable, because it is not it's little difference of what? 0.05. But that notwithstanding, we'll just look at this as what? Unstable. Now go to nitrogen. 14 minus 7 will give us 7. 7 divided by 7 is equals to 1. So that means this nitrogen 14 is what? Stable. But if you divide this, 8 divided by 7 will be 1 point something. 17 divided by 7, 1 point something. So this one is greater than 1. So we classify this as unstable. So they can be what? Radioactive. Are you seeing it now? So that is how to know if a compound is stable or not stable in terms of nuclear chemistry. So back to our reactions. So before we go back to the reactions, we will still look at the camera. Is not clear. I think it's clear enough. So go through your network and see. Please ma explain the neutron. That is what I'm explaining now. Not proton to neutron, it is neutron to proton ratio. Neutron to proton ratio. So we'll divide the number of neutron by the number of proton and see if it is equal to 1 or less than 1 or greater than 1. Then nuclei with magic numbers. What are nuclei with magic numbers? That is nuclei whose proton or neutron are even numbers like 2, 8, 20, 28, 50, 82. We usually call those compounds to be what? Stable. Than nuclei that do not contain this number of neutrons. So if the number of neutrons is 2, if the number of neutrons is 3, it is 8 or it is 4. That is 2, 4, 6, 8, 10, 12, 14. Those are called magic numbers. So, and those magic numbers, if they have it, we'll say it is stable. But if they do not have those magic numbers, it means it is not what? Stable. Then nuclei with even numbers of proton and neutron are likely to be stable than those with odd numbers. Nuclei with even numbers of proton and neutron. Are you people copying the notes? There's no need to copy, just listen. But if you are fast enough, you can copy, eh? Okay, good, good. You can see the board. Okay, thank you. So neutron that has magic numbers, that is even numbers, can be what? Stable or what? Not stable. That is, the one with odd numbers are not stable. The one with even numbers are stable. So I think that is that for neutron to proton, the stability of the element. Stability of the element. Now back to the reactions. So we have done that of alpha reaction, but I will do it again for the sake of those that are just coming. I will do the alpha reactions again before we go through the beta reactions. So for the alpha reactions, alpha radiation reaction examples. Alpha radiation reactions. So let's say example, we have uranium. Uranium is 238 as mass number, then the atomic number is 92. If you bombard this uranium with energy, it will give us tritium of 90 and 234. So how do you balance this reaction? It means you will say +4 and 2 helium. That means the particle it emitted was what? Helium. So what have we done? We have balanced uranium. How do you know that you have balanced it? 234 plus 4 will give us 238. 90 plus 2 will give us what? 92. So this reaction is balanced. In return, this tritium can also be bombarded with energy, or it can also be disintegrated to give another alpha particle. So let's assume it gives us alpha particle. What will be the element of the alpha particle, which is X? What will be the element of X? That means we will say 90 minus 2. 90 minus 2 will give us what? 88. That means here is 88. Is that not it? Then 234 minus 4. Are you seeing it now? 234 minus 4 will give us what? 230. So what is the possible element that is 98? You check through your periodic table. You have to know those elements of your D block. You have to know it. Eh? So if you check through your periodic table, you see that the compound that has the atomic number of 88 is radium. So that means your S is radium. That's what it is. Your S is radium. Now, if radium is your X, and for example you have this other type, you have radium here, 23088. Are you seeing it? 23088. Then let's assume there is we bombarded it with neutron. Neutron is represented as this. There is neutron. Neutron has a mass number of 1, then no atomic number. So that is neutron. So if you bombard it with neutron, what will be your product? What will be your product? Your product will be the isotopes of this what radium, because 88 plus 0 will give us what? 88. 30 plus 1 will give us what? 31. 230 plus 1 will give us 231. But how do you know this is 88? Because in your periodic table, your 88 is what? Radium. So it means if you bombard radium with neutron, you will still get what? Radium. Only that you will not get the isotopes of radium. So that is for alpha particle. So I will give you one example. One example. You do the example before we do the beta particle. So polonium, or let me say, okay, rhenium 86, 230, 224, 224.
Random 226. Random 226.
224. Then I have my element X plus an alpha particle. What will be X? What is X? What is X? So tell me what is X. Then if I have a if I have a can I clean the board? Can I clean the board? Okay. So let's see. Second example, you answer two questions for me. You are answering this radium, and you are also going to answer this now. So what is X and what is Z? What is X and what is Z? So answer that question for me. What is X and what is Z? Okay, I'm going through the comments now for those that are answering the question. Let's see. Chinso said X is 88. But you didn't complete it. Is it the atomic number that is 88, or it is the mass number that is 88? You would have indicated. So Chinso, you are not with us. Williams said it's radium. So what type of radium it is? Is it, what is the max number and what is the atomic number for the radium? Is it the isotopic radium or is the stable radium? So you need to indicate that too. Okay. Then Esther says, ma, in exam condition, when we are balancing the alpha radiation equation, is it necessary we write the exact element, or we can put an alphabet with the correct mass number and atomic number? Yes, it is necessary you put the right element. It's necessary you put the right element. But if you don't still know it, just you can use an alphabet to represent so that you don't miss any of the mark. At least you get half mark. Okay. Egosa. Yes, Egosa, are you right? Yes, Egosa is very right. Yes, Egosa destiny is very correct. 220 for the mass number, and 84 for the atomic number. Chinso, you are also very correct, but you have not told us whether it is Oriano or is Polonium. So what is the element? What is the element? Chinso, what is the element? Egosa, what is the element? Eunice, yes, Eunice is correct. Eunice gave us the exact correct one, which is polonium. Polonium is the element, and it has the atomic number of 84 with a mass number of 220. Then Eunice Osarem, if I can't pronounce it, please pardon me. You are also correct, but if you look at that first one, what is Z? You have deleted it, okay, because that is not correct enough. Okay, thank you for. So that means we are following, we are on the right track. So okay, x is 220 with the mass number 84. Like I said you will simply say 224 minus 4. 224 minus 4 will give us what? 220. 86 minus 2 will give us what? 84. So what element is having 84? It is polonium. Po. Represented as Po. Polonium. But for this one, many of you didn't get this one at all. None of you got it, but I will give you time. I'll give you time. So what will be the answer now? Let me see those who have solved it. 8 and 4. Yes, you are on the right track. Not that you are wrong, but you are wrong, but you are on the right track. It cannot be 8 and 4. It is 8 and 4, but it is not represented as 8 and 4. So let me see. Ma, sorry for taking you back. The nature of the alpha, beta, and gamma, the 4 and 2 means what? 4 means mass number, 2 means atomic number. That is for alpha. That is an alpha particle. But for beta, it is 0 and -1, and gamma has no number. Okay. Many of you are right, but you are just putting 8 and 4, but it's not 8 and 4 I'm expecting you. Yes, I've gotten someone who gave me the right description of what I'm looking for. 2 moles, that is Danny Bars. Danny Bars is very correct. 2 moles of helium particle. 2 moles of helium particle. 2 alpha, yes, 2 alpha. So that is it. So it means we will say is what? 2, that means your Z, is 2 helium particle, which is 4 and what? 2. Because 2 times 4 is what? 8, and 2 times 2 is 4. So when you add it to it, 230, it will give us 238 and 92. Thank you so much. So we'll go to the next one, which is what? Balancing up with gamma particle with beta. We'll give example for beta. Beta, the symbol of beta is there. This is the symbol to represent what? Beta, 0 and -1 reactions, beta reactions. Beta reactions. Like I said before, beta reactions is that it has no mass number. It is negatively charged. It decreases the atomic number of an atom, and thereafter it is stopped by aluminum foil paper. It has a penetrating power of 100, and it cannot be stored by tin paper. So what are the emissions of this gamma? How do we represent them? So let's look at it together. So I will take a very simple one, simple reactions, and see how we can do that of so let's take for example we have carbon. Carbon is 14. Isotopes of carbon is 14 and 6. It means I will have carbon which is 14, then the atomic number will increase. That is plus 0 minus 1. So 14 plus 0 will give us 14. 7 minus 1 will give us what? 6. That is how to show that beta relations are what occur when you combine this with so let's see potassium for example. Potassium. Potassium has atomic number of 19. Thirty-nine, 19. So when you bombard potassium with energy, what will it give to you? Sorry, I'm trying to get my marker together. Okay. We will have 40. If we have a 40 and we have 20. 20 is what? What is 20? 20 is the first 20 elements, and 20 is calcium. You have calcium. So here now, how do we balance it? It means we have a beta emission and we have what? A neutron emission. So that means you will now balance it. Sorry. We have 39 C20, and that is calcium plus what? 0 minus 1. So you see that the atomic number increases, is increasing. So minus 1 will now help to decrease this atomic number to give us what? 19. So 20 minus 1 is 19. 39 plus 0 is what? 39. So I will now give you your own question on beta reaction. So let me go through the question and see. So do we understand? Z does not have a number. Z has a number. 2 moles of alpha particle is Z from the previous question. Then this person is telling us Williams. You said you are supposed to find it. Yes, we know. Calcium, yes, it's calcium. 2 atoms of helium, yes, 2 atoms of helium. So we are on beta particle. For the beta particle is clear. If you look at the board, we said 14 carbon, 14. The mass number of carbon is 14 and the atomic number is 6. So when it emits, it gives us 14 and 7. So 7 is not carbon. 7 is not carbon. Thank you for that correction. 7 is not carbon. But what is the atom that has atomic number of 7? That is what? Nitrogen. So when carbon is bombarded with energy, it emits nitrogen. So what will balance the reaction is what? What will balance it is what? Beta. 7 minus 1 will give us 6. 14 plus 0 will give us what? 14. That is how beta particle is balanced. Same is applicable to this. Potassium. This is potassium and this is what? Calcium. Calcium is 20, potassium is 19. If you had a beta particle, it becomes what? 20 minus 1 equals to 19. So can I give you my own question now for you to solve? Beta particle does not consist of neutron, but a reaction can undergo neutron bombardment. A reaction can undergo neutron bombardment. Yeah? So let me drop my question for you. So let me drop my question for you. You do this for me. Palladium is 91 with 2, 3, 4. What is Z if it emits -1 E? So beta particle can be represented so that you don't get confused. It can also be represented with what? E as electron or beta as the symbol. So if you see E, it means it's beta particle, provided what you are watching out for is what? 0 and -1. Are you saying 0 and -1? Saying that the mass number for the beta particle is 0 and the atomic number is -1. Okay, then you will now do this for me too. Let me use Y to represent. It's not proper to use Y. Let me use G and the 0 -1 E. Then lastly, I'm thinking of a compound now. Let's say your G now. What is W? When you have gotten your G, what is W if it emits a neutron? So what is W if your G emits a neutron now? One with mass number of 1, atomic number of 0. So I'm going through the comment to see what you have dropped there. So I'm waiting for the question. I'm waiting for your answers. Let me go through the comment section. I'm going through the comment section to see. Okay, so I'm going through the comment section now. Ogene divine. W is an isotope of palladium. Yes, W is an isotope of palladium. Good. That's very correct. Thank you. It's very correct. Then Z is 234 and 92. Well, and what is the 92? You need to tell me what 92 is. That is Emmanuel Osemudiame. Tell me what is 92. Then magnificent palladium 230. Good. You are very correct. You are very correct. Okay. So that means we understand beta reactions. We understand beta reactions now. So we are going to look at gamma reactions. You know, for gamma reactions, there will not be any kind of changes, because gamma does not have a change. It does not have a charge, and the the mass number is zero. The atomic number is zero. It's an high photon pack of energy. We know that photons are called pack of light energy. So gammas are just lights. They are lights with no charge. Light with no charge. So we said here that the Z is, here is 92. So 92 is uranium. Uranium is 92 with the mass number of 34. So we can simply put it here as what? Gamma. So if we put gamma, it means there's no change. It means there's no change in the reaction. What is the reactant will give us what is the reactant. That is what it is. So gamma is very easy to balance. Here we said is what? Y. So if there is Y, that means here remains what? Thorium. Here remains thorium because it has no charge. So if you say, if here is a potassium, for example, potassium is 3919. That means with gamma emissions, potassium will still be 39 and what? 19. So gamma reactions, beta reactions, and alpha reactions are already given. What next is, if a compound, now we'll take this question together. Let's take this question together. If you look at our past question, Jupe past question, they asked us, let's take the question together. A nuclear reaction, a nuclear reaction that powers a radioisotope thermoelectric generator. Are we taking the question? Let's take a question together. Please, I want you to jot down this question. Jot down the question. Write a nuclear reaction. Write a nuclear reaction for each step of the formation of polonium and uranium. Let me write it on the board so that everyone will follow suit. So just hold on a minute. Let me refill my marker so that I can write the question. I can write the question. Let me refill the marker so I can write the question while I take some comments. Praise said, please ma, solve the last question. We have solved the last question now. W is somebody gave us in the comment section and I told you it's correct. Hmm? We said W is palladium. Is that not it? Palladium. How is it palladium? Nothing changes. Nothing change. Nothing change. Only is the isotope of palladium. That means you just needed to add one to the max number. You just need to add one to the max number. Hmm? You just need to add one to the max number, but it becomes an isotope of palladium. Becomes an isotope of palladium with the max number of 233. So Grace have said it in the comment, and Grace is correct. Grace is very correct. Grace is very correct. So we are going to take this question together. After taking this question, we will now do some calculation based on binding energy. No, atomic number. I'm seeing praise Idahosa saying palladium max number is 234. Atomic number is 92. No, atomic number of palladium is not 92 but 91. And the max is uranium that has a max number of 92. So we'll take the last question on nuclear chemistry, and before we go to the energy. He said, write write a nuclear write a nuclear reactions write a nuclear reaction for each step of the formation of 218 84. 84 is polonium from uranium. Uranium is 92 and it's 238. That is the atomic number. Hmm? Which proceeds in the order of alpha, beta, beta, alpha, alpha, and alpha emission. So can someone do that for me now? So before we move to the next step, do that question right now before we move to the next step. So this question you will snap and send it on the comment section. The question is, write a nuclear reaction for each step of the formation of polonium. Polonium has the atomic number of 84 from uranium of atomic number 92. That polonium, the mass number is 218. The uranium, the mass number is 238, which proceeds in the order of alpha, beta, beta, alpha, 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 and alpha